We're back with more gas relationships, and this time we're looking at pressure versus temperature. This relationship is defined as when temperature increases, pressure increases, when the volume and the moles are constant, or the amount of gas. Macroscopic example of this would actually be the can versus gas. We actually looked at this in the opposite way. In this case, you had the can that was heated, it was flipped over into the ice water, and the pressure decreased in the inside of the can, which is why it imploded. Symbolic relationship for this. Again, we're going to look at a graph. Okay, temperature increases, pressure increases, volume and amount of gas are going to stay constant. So here, I'm going to draw my axes. We've got temperature, and this was in degrees Celsius. Pressure is here. This is what our graph looked like. Okay, did not pass through the origin. I am going to sketch this out a little bit more. Yikes. Okay, to show where we would have zero pressure. And this is going to have to be at negative 273.15 degrees Celsius, which is 0 Kelvin. And that's going to be because we have no motion of particles because of the temperature, right? This relationship is linear. Okay, if we look at the relationship where we are actually in Kelvin, so whoops, let me move that axis up just a little bit. Okay, I'm just going to make this one little. So when we do have absolute zero as our origin, then this is going to be linear proportional. And remember, we are going to find Kelvin as scale as absolute. Okay, particle diagrams. We want to show that our volume is the same. So again, didn't do my very, very best, which that was not very great, to draw two equally sized containers. Same number of particles. Again, 4 or 5 is probably a good number. Let's switch it up and go with 5 this time. Whoops, that one's a little small. And then 1, 2, 3, 4, 5. Okay, so pressure needs to increase. Temperature is going to increase, okay, which means we're going to show a change in the number of collisions and a change in the number of whooshies showing our motion. So I'm going to start with one whooshy line in my first box on the left, and I want to show a couple of collisions to show our pressure.
Good morning, Carmel High School. This is Mrs. McDaniel. Just checking in, thanking everyone for your quick response. A student had accidentally hit the alarm. Fortunately for us, we have cameras on our alarms, so we're able to identify the issue quickly and get you back into class. So thank you very much for your cooperation and how timely you were. Thanks again. Have a great day. Bye.
Okay, so one whooshy line to keep it consistent. Let's go with 2 collisions here. Now, speed of the particle changes when the temperature increases. So we're going to show more motion. More motion is going to be mean that we're going to have more frequent and forceful collisions, both with particles and other particles and particles with the container. So I want to show more collisions and more motion. So 2 lines for both whooshy and whammy, and I want to increase the number of whammies to show the collisions. So I'm going to go from 2 to 4. So I'm going to show 2 lines for each of my whammies. Let's go maybe 1 here. Let's go 1 here. And then this particle is still moving at a higher speed, so it's going to have more tails. All right. So let's show what we've got. Same number of particles. And volume. We've got slower motion and fewer collisions. Whoop. Let's try again. Fewer versus faster motion and more collisions. That's why we have an increase in pressure. Okay, so that's going to take care of our pressure relationships where pressure is the dependent variable. Let's now take a look at volume versus temperature. Volume is our dependent variable, temperature is the independent variable. So what we want to say here is that as temperature increases, volume will increase when the amount of gas and the pressure are constant. Okay, perfect example of this is the balloon and the hairdryer, right? This is going to be because of expansion and contraction. Because of our change in volume at the macro level. And let's see if I can do my best to draw a little balloon and hairdryer. Gosh, I can't spell today. That's fine. Dryer. Let's say there's our balloon. We're going to heat it up. I'm not going to try to draw a hairdryer. I'm just going to draw like the sun. Okay, so let's make it yellow so you know that it is. And then we're going to show that this is a larger volume. Okay, symbolic relationship here. Temperature increases, volume increases, pressure and amount of gas are going to stay the same. Okay, here I want to show my graphical relationship as temperature in degrees Celsius, which is versus volume. Again, we're going to kind of see the same thing. This is going to be linear. Okay, if we show that with our absolute scale of temperature in Kelvin versus volume, then we're going to have linear proportional. Okay, finally, particulate. Yikes, smaller volume, larger volume. I'm going to go with 4 particles. Okay, I'm going to show my collisions and my speed. Let's go 1 line and 2 collisions to show my lower temperature. Pressure has to stay the same, amount of gas has to stay the same. So I want to show 4 particles and 2 collisions. The difference here is I've got a higher temperature, so faster moving particles. So I need to show 2 tails on my 2 collisions and then 2 tails on my particles for motion lines, right? So same number of particles and volume. They're moving slower here, faster here, and whoops, not the same number of volume. This is the same pressure. Okay. The increase in volume comes from those particles colliding more with each other and with the container as that speed increases, and that causes the particles to move apart, which is why the volume increases and we see the expansion happen.